Welcome back, everyone, and we're back, and we're going to do some more particles. This video was meant to be about producing a field of grass, but to produce grass, you have to do something called billboards. And after a while, I really thought it kind of deserves its own video, so I'm going to try to record two videos tonight. One just on billboards, and then you'll see another video, hopefully tomorrow, with actually doing the grass that uses billboards. But the topic really deserves its own video because there's not a lot to it, but there's quite a bit to explain about billboards. And on top of that, I also have our emitter rebuilt to be used in a more easier way. So you might be asking, maybe you do know what billboards are, or maybe you're here and you're like, what are we talking about billboards? Billboard is a term in which you know what a billboard is. It's a billboard sign that you see out in the roads. It's a big old rectangle or square. It's a big old thing that just advertise, right? It's always kind of like staring at you. And I don't know how the term is used for 3D graphics, but the idea of billboards is that you always have something facing you specifically. So right now we have our particles from our last video. As you can see, it looks fine. Everything's facing us. But when we start rotating, then you start noticing that it's a quad. And when you face it this way, then you just can't see it anymore. It's barely visible because we're kind of looking at it from top to bottom, and it's a quad, so it's hard to see. So the idea of billboarding is that you automatically rotate these quads to face the camera. So no matter what, they will always face the camera no matter which angle you see it in. So that's what we're going to deal with. We're going to deal with that. And there's actually two types of billboarding on top of that. So we'll quickly discuss the two types, and we'll look at the code for the two. So first thing, let's look at our new emitter, something that I cleaned up all the code from the last three videos. We were using raw WebGL. Now I've abstracted all that away. So we got a new class that's in our test file. I'm calling it mesh emitter. Previously it was called emitter mesh. It has a lot of the same things. We still have our material for the feedback loop, draw mode. We have calling turned off. I think I renamed a couple of things. Now I'm doing element count, is basically how many vertices are in our mesh. So I'm just calling it the element count because it can also be the elements index array. How many particle counts we're doing. This is basically how many instances we want to do of our particle. I guess element count, I guess you can say it's how many vertices that makes up our particle. Okay. We have our VO draw. That's the VOs that handle our drawing. Read feedback is the reading aspect of our feedback, and write transform feedback is that. So when we create an emitter, we're going to pass in like a boatload of information on how to set up the buffers. And we'll start off with the setup function. You tell it how many particles we want. We're going to pass in our index buffer data if it's available, and then we pass in just all our buffer information. And then, what we do is save the count, we set up our buffers, we set up our feedback, and we set up our draw VOs. So everything is not instead of one giant function like we've been having, now everything's kind of broken out, and like it's easier to manage. Like a lot of the code is all the same, except it's all organized differently. In this incarnation of it, the first thing we're going to do is we're going to set up all the buffers. We're going to just set up all the buffers, be it read buffers or drawing buffers. If it's a data buffer that's on the GPU, we're just going to create them all and save them into an array in the object. We're going to save it into this.buffer. So that's all this does. And it does the index first. Because index is a separate type of buffer. So that's why you only can have one anyway. So that's the reason why I have it done as a separate condition, and everything else is treated the same. Everything's treated as a float 32 array buffer. So once all the buffers are done, and then we can assign all the buffers to our feedback information. So this way is where we actually start binding our buffers to VAOs and to the feedbacks. And setup draw video is the same thing as the feedbacks, except now it binds it to the drawing VAOs instead of the reading VAOs. So it's really just kind of cookie cutter repeat, code. But like I said, it's everything more organized, and it loops through the data that we have. So now we have three. So we have those three functions that really builds up all our VAOs, buffers, and feedbacks. And then at the very end, we have our draw function. And our draw function is clean up a bit. We activate our first shader. We pass in time. This part actually handles the computing part first, and then we do the rendering and we do the cleanup. Nice and clean. Everything's commented, so everything makes good sense. So that's our new emitter that we can use moving forward. And this is what the data looks like. So just like in previous, we have all our data. We got our index, we got our vert because we're building a quad. This is the UV for our quad. And this one looks strange. This is kind of like new ES6 stuff. What this does is initiate an array that's blank. So it builds me a whole array that's blank, and then I use JavaScript functional programming style to kind of fill it in. So that's why the for each, and then I have I don't know what these are called. These are called delegates to me for like C#, but these are like anonymous functions, shorthand anonymous functions. I forget there is a name for it in JavaScript, but so for every empty element in life, I kind of fill it in. And this one, I'm just doing like a random number for life. And then, this is the same thing we did in the previous video where we just had a regular for loop that goes through it. Now I'm just kind of using functional programming style to do it using ES6 and I think ES5 functionality. I think for each was part of ES5. And ES6 comes with a bunch of new ones like this shorthand for creating completely empty arrays. Like if I want like 10 elements, it'll give me 10 elements. I think if it gives me undefined, then I got to go in and fill in all the values. And then this is our buffer information. So this is what we kind of just throw into our emitter, and it ends up building all our buffers. Like that huge global code we had for those three values gets all compressed down to this, and then this emitter actually reads that information and builds it all up. So we give each buffer a name, we give it its component length, we can pass in data. If we pass in null, it would actually create the buffer as an empty buffer and just calculate how many bytes that's needed. So it does that all for you. So if it's null, it automatically calculates it. Draw location in our shaders, our read location for our shaders, and our write location. Because the values can be different, and don't forget these buffers are shared amongst a bunch of shader VAOs and a bunch of feedback loops or transfer feedbacks. Inst means is it instanced? So when it starts binding it to the draw buffer, it knows to use those buffers as an instance buffer. I have used in. I'm using like binary flags. I guess that's what you might call them. Binary flags to kind of denote how things are. So 1 means read, 2 means write, and 4 means draw. So if I want a buffer to be used in all three, I add them all up, and that equals 7. If you're used to like C++ and stuff like this is very common. These are flags. C#, they're in there sometimes too. In case you don't know, it's just binary operations. A quick example right here. If I'm doing setup feedback, I look at B used ampersand, single ampersand 1 not equal 1. So basically, if used in binary bitwise and 1 equals 1, that means that 1. What does 1 mean? 1 means read. So that means basically I'm saying I'm looking for if it does not equal 1, just ignore it. Just continue. That's what I'm doing. So it just continues because we only want to bind buffers that are set up for reading. So that kind of allows us to make it very easy to facilitate data, like how to assign something. Normally in like C++ or other languages, you would kind of create an enum. Something like this. I'll just say, I probably shouldn't waste my time because this is JavaScript. But a smart way is to basically maybe build some kind of structure like that. And then the idea is that when you combine them, you can always do something like enum.read. You can do something like this in JavaScript too if you really wanted to. Enum.read. Something like this. This is like pseudocode because I don't remember how to write an enum in C++ anymore. So to make it like more user friendly, you'll probably do something like this in your library. You kind of create like a struct, then you're applying the values, and then you can use the single bracket to combine the values. So if you say read that and that, it should create a value equals 3. You can also just do this, to be honest. You can just add. If you don't want to do binary operations, you can just add them up. They produce the exact same value, so it's 3. So when I start doing bitwise operations to pull out the values, I can then tell which buffer, where should this buffer be used. So yeah, that's essentially what I'm doing here. It's a lot of binary BS. Low level programming. Gotta love it. Because like I said, it's not something you normally see in JavaScript. But if you guys are JavaScript programmers, you're probably not used to doing binary and bitwise operations. But you should definitely get into it because with WebGL we do a lot of byte handling. So it's good to know how to use bytes, bitwise operators. And the usage is just a copy of what type of usage that buffer is going to have. These are dynamic copies because these are going to be modified on the GPU. Static draw means that. And I'm using them that way. So this way, when I bind them, where's a nice example? Be right here, I think. Where do I bind? When did I say buffers? It might be when I actually create the buffers, right? Create buffer, bind buffer, buffer.name. There it is. Data buffer. It gets the context and then the usage. So instead of me just typing something like gl.ctx.static draw. I don't know if you ever saw me do it this way, but in JavaScript you can access any struct as a named index. So technically, I can also do something like this. In case you didn't know, you can do this in JavaScript. So I can make it into a string and then use like an indexer operator to actually get that value. So since that's the string, I can then just put it into a variable. So this way, I don't have to do like if statements. I don't have to create enums or anything. It's kind of like a quick shortcut to just to do it. And like again, it's more user friendly to be able to see text compared to like these, which you kind of always have to look up. That's why I kind of show you that example. Like if you're gonna do it in a library, maybe you should set up enum type of things. So this way you can combine them to make them easier to read when you look at the code. 'Cause you're gonna be like, man, 7. What does that mean again? That's why I kind of wrote my notes so I can look it up. And that's it. And you always have to make sure, and then you pass in the data when you need it. And I think that's all. That's it. And once you have your buffers, you pass it in, and it creates our emitter. So I think I spent enough time talking about the new emitter. So that's why. So the next video when I do grass, we don't have to worry about all this BS. So now that when you see this stuff again in the next video, it won't be like, what the hell is it? All right, so that's that. So if we go into our Transform FBP2 shader, this is the one that does the actual drawing, we are going to show you how to, or I'm going to show you how to do billboards. And I saved the link here for an image. I forgot to load it up to illustrate an idea. There we go. Now, what you see, you don't know if you can notice what this is, but this is a transformation matrix. I think here, and here, M0, M5, M10, that handles our scale. These are our translations, and I believe was 0, 8, 10, and 2. No, if these three are our scale, then the remaining ones are a rotation, I believe. So it's 1, 2, 4, 6, 8, 9. That handles our rotation. So this is our entire transformation matrix that does scaling, translations, and rotations. What you might not realize is that once you have the transformation matrix all set up, all calculated together, you can actually get the axes of direction. So this part of the matrix actually is the left or right, depending on how your point of view. That's up and that's forward. So if we want to, let's say, so that's like this, so we can find a direction by simply pulling out the information out of the matrix. I think we've done this before in the past using the look at function. So since we have the matrix sent into our shader, like through here, our camera view, our Mat4 camera view, that's our transformation matrix for the camera. So this way we can view everything. Now, the thing you probably don't remember at this point, this is it. The camera view matrix is the camera's local matrix inverted. In case you don't remember, why is it inverted? It's because the camera does not exist. The camera is not really an object that's on the screen that you move around, and then it just videotapes what you see on the screen for you. That's not what a camera is. In case you haven't seen that video about cameras back in the very beginning of the series, cameras don't exist. The way the cameras work is that you have an idea of where the camera is moving, and then you move the entire world the opposite way. So if the idea of the camera is to take 5 steps back, you're going to get inverted and do 5 steps forward. And this way, all the objects in your screen and your scene will get moved 5 steps forward, even though the camera technically is moving 5 steps back. But like I said, you're simulating the idea of a camera. So now you keep that in mind, that this is the invert. So if our camera, so this is our camera, we're 5 steps back, and we're looking at let's say we're looking at the effect. We're looking at the pixels. We're at the particles, right? We're looking right at them. So our local matrix shows that the forward motion is from me to the screen, to the particles. Now, that's the local matrix. But when we bring it into the shader, it's inverted. So the real forward direction now is the particles staring at me. Since we have that matrix on there, so we already have all the information we need to calculate the forward direction for our shader, for our particle. So, like, think about it. The camera, I'm looking into the scene, and the inverted matrix is the scene staring right back at me, perfectly staring right back at me. And that makes things so much easier. So that's what this part is right here. We're grabbing the right, which is really the left. You know, remember this one image. Here's the left, and here's up. So that's what we need. We just need the right, and we just need up. So once we have, and we make them into vectors, and they're already they should be, I guess, normalized. Maybe not. I'm not sure if they're normalized or not. But yeah, you pull out the right direction and you grab the up direction and the right direction. So right now we have this one set up. So we have pose, adding offset. We're doing no billboarding. So if I comment this out and then comment this in, now mind you, billboarding is based essentially just these two lines, this line. That's all billboarding is. It's just getting two directions and then applying those two directions to your position. Now this math is a little wonky, kind of like. Let me try to explain how it is. This billboard math only kind of really works on a quad, and it kind of only really works very well when the center is at origin. So with the center being on origin, all the points is basically all the points on your quad is the distance away from origin. So that allows you to kind of define how far you want to move in that particular axis. So by using the A offset as the new center point, so let's say we're moving away from origin and we're going to a new center point. So that's our new center point that we're moving the particle to. So we're going to say that's our new origin plus the right direction that we got from the matrix, which is the inverted matrix from the camera. And we say we want the right times x. So x is going to be 0.5 or negative 0.5, depending which side of the x I'm on in the quad. So it'll be that whole thing times that plus offset. And the same thing with y. So it's just how far from the center it's going to be. And it essentially basically, the idea is that this tells me which direction I want to go to. And this one's kind of like the radius from origin. This should be. So I want to go right, the distance from origin, the up direction, distance from origin, and you add all that up to the brand new origin. And that's how this math works. Now, why does it work that way? Not sure, because I'm not a mathematician, but that's what's going on here. It's like I said, this is the direction. It's like we've been doing before when we want to we were doing like raycasting. We would get the raycasting like the normal direction, but then we say, okay, that was normalized. Now, but we want to go 5 units forward. So we take that normalized value and then we multiply it by our length to actually get the actual length vector. So that's basically what we're doing. We're taking this unit vector, which that's why I'm thinking it's really a unit vector. This unit vector, multiplying it by a scalar value, which then gives us the actual position this vertex needs to be. So if I click save, come over here. So now remember, it does not follow me. So if I go here and just empty cache and start, there goes our particles. Now no matter where I rotate, the particles are always staring at me. I'll never actually see the edges of the quad anymore. And what this is called spherical billboarding. Spherical in the sense that you can rotate anywhere in a 360 pattern and in a 360 direction, and this the particle or anything. Like I said, this works mostly with quads. Or actually any 2D, I shouldn't say good quads, any 2D objects, essentially. This is really good for 2D objects. So any 2D objects will always face you at the camera. Now, this is great for particle effects because you always want the particle staring at you. Now, let's say if you want to do cylindrical. Now, cylindrical, let me finish explaining this. Like this is spherical, right? So the idea is that you're basically rotating by X and you're rotating by Y. It's kind of like a gimbal thing. So if you think of like a tank, Now you can have I have a tank cannon, and it can spin around, and then you have the barrel that can go up and down. So the Y is the barrel going around in a circle, and then the X is the cannon thing, the barrel going up and down. So that's essentially what you're doing. You're doing these rotations right here, and that gives you that 360 direction that you can get. Now, if you want to do cylindrical, a cylindrical is like a cylinder, and that means you're only using one axis of rotation. So in this instance, we want to basically reset the up position. So that means we're not going to rotate by up anymore. We're only going to rotate by X. So that means we're only going to spin around in a circle, but we're not going to look up and down. So if I empty cache, now you can see the particles are not staring right at me, but no matter how many times I rotate, it is always looking at me on the X plane. Actually, no, it's the Y plane. So it's basically doing a Y rotation. So no matter where I'm going, it's always going to keep that Y direction facing the camera. Now, why does it matter to have two different types of billboardings? Well, when you're dealing with, let's say, particles and UIs, you always want it facing the screen. Images. OpenGL Health UI. I think that might be it. Can I find something good? I really should look up these images. Like I said, I'm kind of just doing these things on the fly. Oh, you know what? Game UI over character life. Gee, I'm not having much luck. Oh, why not? Oh, there we go. This is what I was actually looking for. So billboarding. So not just for particles, but sometimes for actually UIs. Like, see the life bar of a character. No matter what rotation your camera will be, that will always be flat facing you. So that's another good use for billboarding is. Like, that's what kind of meant for any 2D object that you want to kind of stay 2D but always facing you, so you don't rotate and you can't see it anymore. So that's another reason, another good use for spherical. Yeah, that's a good use for spherical billboardings. Now, cylindrical billboardings, billboard grass. Now, billboarding cylindrical allows you to build grass very easily in the 3D world. Maybe this is a good example. Basically, it's kind of like that. So you always have this, right, like staring right at you, but you can kind of scroll up, and it'll look more realistic that way. So like for things like maybe trees or grass or other type of foliages, the cylindrical billboards works really, really well. In the next video, you get to see that. We're actually going to build kind of grass kind of like this a little bit. And you'll see that works very well. But if we're going to use spherical on grass, it'll look horrible. It looks really, really bad. So those are the two purposes for billboarding. You know, it's like I said, one's for UI. Sometimes you need it for particles, like certain things like grass. And there's like a lot of other things in 3D that you might need it. I just can't picture. I just can't remember at the top of my head of all the little instances of it that you need billboarding for. But it helps you a lot. Like I said, definitely UIs, kind of like all kind of UIs. Like if you ever hit a character in a game and you have a little text that bubbles up saying, okay, you get 10 hit points, 15 hit points. That's all Billboard. You want that to be billboarded. If you're doing a multiplayer online game and you have the character's name is on top of the character, that's also going to be, you want that to be billboarded at a spherical way. So this way it's always facing the camera, so it's always easy to read and it's always visible. It's always in the viewing angle that's perfect for you to see it. So yeah, so there you go. And that's it. That's, like I said, that's all really to it. It's just these 4 lines of code pretty much describes your 2 billboarding features, and it really comes from our camera matrix. If you don't have a camera matrix, I guess there's other ways to go about it, but it's much more complicated. You have to do like cross applies and whatnot, and you kind of need the camera position, and you don't want to do that. It's better off. Like, you will always need a camera matrix. You will always need a camera matrix, so you don't have to worry about it the more complicated way. This is like the easy way. It's the information's already there. It's already inverted. You already have the information that tells you where to face the camera. You got to pluck it right out, and then you can use it in your kind of like your rotation equations. And that's it. So I'm going to stop this video, and I'm going to prepare myself for the next video. So you guys will get both videos this week on billboarding, and then the next one will be grass. We're going to make grass. So I guess like and subscribe. Like really help me get more subscribers if you can, really, because I really want to get that silver YouTube award. I just want something on my wall that says Sketchpunk Labs did something great. So yeah, I'm not waste too much time because I gotta make another video tonight. So like and subscribe. See you guys in the next videos. We're gonna make some grass.